This video is actually about the details of Rice's theorem. So this is Rice's theorem, and we'll have a look at the function version. At first, I will give a formal definition of Rice's theorem, and I will define R. R should be the set of all Turing computable functions. So let R be the set of all Turing computable functions. And then we take our specification S. Let S be a non-trivial subset of R. That is, S is a subset of R. S is not the empty set, and S is not the set of all functions, of all Turing computable functions. Then it is undecidable. If a Turing machine computes a function in S. In S, formally, the set CS is the code, is the set of codes of Turing machines. So again, we have binary encodes of Turing machines such that the Turing machine computes a function S. Function in S is undecidable. And it is undecidable for all but the two trivial cases. First, we'll have a look at why the trivial cases are decidable. If S is the empty set, then the problem is decidable. The answer is always no. Is always no. And if S is the set of all functions, then the problem is also decidable. Is decidable. And the answer is always yes. Yes, of course. Because any Turing machine computes some Turing computable function. So if it's the empty set, as it computes some function, yeah, it's the answer is of course no. And if it's the set of all functions, then the answer must be yes. So these are the two trivial cases. Now we can proceed with the proof for the general case, for the non-trivial sets of functions specifications. And we will do the proof by case distinction. And for the case distinction, we'll need something specific, and this is the function that's undefined for all inputs. So I'll call it bottom, be the Turing machine computing, no, not the Turing machine, be the function, sorry, be the function that is undefined for all inputs. inputs. This function is, of course, Turing computable because it's computed by the Turing machine that never halts, that has an infinite loop. This function is computed by a Turing machine, for example, that only has an infinite loop, that only contains an infinite loop. An infinite loop. And for the proof, we'll do a case distinction, distinguishing two cases. The first case being that the bottom is in our specification S, and the second one that it's not. So the first case, case 1, is the case that bottom, the function that's undefined for all inputs, is not in S, not in our specification. Okay, now we have a set of functions. As this set is not empty, there must be at least one computable function inside. So as the set S, our specification S, is not empty, there must be a function Q in S. There must be at least one function in S, and this function must be computable, so for which Turing machine Q exists that computes Q, small q, that computes a lowercase q. So there must be at least one, and we just fix this one. Okay, now what we do is we construct a new Turing machine. We have this Turing machine Q here, and we'll use this Turing machine Q to construct a new Turing machine. And this new Turing machine will do the following. This Turing machine receives an input, x, and the first thing it does it simulates some Turing machine, MW, on the empty tape. So we just take one Turing machine, MW, and we simulate it on the empty tape. This is the first step. Afterwards, we do a second step, and in the second step, we start Q. So if MW terminates, or halts, we start the Turing machine Q to compute Q of x. And this is the second step. And this step is actually performed after the first one terminates. This can be realized, for example, by a two-tape Turing machine. This is a variant of a Turing machine with two tapes. Then it's easy. You just save the input on the second tape, simulate the Turing machine MW on the first tape, and then simulate Q on the second tape. Okay, now we have constructed a Turing machine like this. And if we have a closer look at this one here, the blue one, it says we simulate MW on the empty tape. And that actually looks like we would like to decide whether MW holds on the empty tape or not. And this is actually what we would be able to do now. Let's go through the cases together. The first case is what happens if W is in H0. This means that MW holds on the empty tape. On the empty tape. If MW holds on the empty tape, this means that eventually this first step stops and eventually Q is started. So if MW holds on the empty tape, then this Turing machine here actually computes Q of x. Then this Turing machine M prime, then M prime computes Q of x, because then it would start this Turing machine Q. But if it computes Q of x, we know that then this means that M prime computes a function in S, because Q is in S. In S. So that's the first case. Let's see what happens in the second case. If W is not in H0, this means that MW does not hold. Not hold on the empty tape. Okay, if this Turing machine does not hold on the empty tape, this means that the second Turing machine is never started, because the first Turing machine does not terminate. If the first Turing machine does not terminate, this one is never started, and our Turing machine M prime does not terminate. So the Turing machine M prime does not terminate for any input. Because regardless of our input x, as our first step, we simulate M prime on the empty tape. This means it doesn't matter what we have it as an input here. If this Turing machine does not terminate, our Turing machine M prime will never terminate. So we know that if MW does not hold on the empty tape, then M prime does not terminate for any input. If it does not terminate for any input, this means that the Turing machine M prime computes a special function. And this is then M prime computes the function bottom. Because bottom is the function that's always undefined. And the function that's always undefined is computed by a Turing machine that never holds. So in this case, we would have M prime compute the function bottom. If it computes the function bottom, and bottom is in our case not in S, then we know that M prime computes a function not in S. Function that is not in S. Is not in S. So in conclusion, we know now that for some arbitrary Turing machine, W, this Turing machine is in H0 if and only if the Turing machine M prime computes a function in S. So actually by this construction we would have a means to decide whether a Turing machine actually holds on the empty tape. But we already know that this problem is undecidable. So the problem whether a Turing machine computes a function in S must be undecidable as well. So we can conclude that in this case this problem cannot be decidable. So as H0 is undecidable, we know that for case 1 it must be undecidable if a Turing machine computes a function S. It is undecidable. Decidable if a Turing machine computes a function S. In S. And this concludes the first case. For the second case, we just consider what we have to change. The main point of the first case was that if our Turing machine MW holds on the empty tape, it means that it computes the function bottom, and if it does hold on the empty tape, it computes the function Q. So we would like to maintain this distinction, and now we have to consider the case. So it's case 2 now, and now it's the case that bottom is actually in S. So if bottom is in S, we need a function that is not in S to maintain the distinction. So we would like to have a function Q that is not in S. And the reason why there must be a function that is not in S is that S is not the set of all computable functions. So S is not the set of all functions. As S is not the set of all functions, there must be a function that is not in S, and it's still Turing computable. So for which we have a Turing machine that computes this function. And now we keep the very same construction for the Turing machine and see what happens. So if now in this case, if W is in H0, it still means that this Turing machine hold on the empty tape. If it holds on the empty tape, then this Turing machine Q is eventually started, and this Turing machine Q computes Q of X. So in this case, this combined Turing machine still computes Q, which now is not in S. So this is a function that is not in S. On the other hand, if W is not in H0, then this Turing machine here will never terminate. As it will never terminate, regardless of the input, the whole combined Turing machine will never terminate. So the combined Turing machine M prime will compute the function bottom. It's the same here. However, the function bottom in this case now is in S. So we now have the case that M prime computes a function that is in S. So not that much actually changed. Now we go to our conclusion. Now we combine both cases, and we know that W is in H0 if and only if M prime computes a function that is not in S. However, it doesn't really change anything. We just have to toggle the output, and we still would obtain an algorithm to decide whether a Turing machine holds on the empty tape or not. This problem is known to be undecidable, in this case as well, of course. So we can conclude that also for the second case, this problem cannot be decidable. And there are only these two cases, because either bottom is in S or it is not in S. And for both cases we have derived that it could not be decidable whether a Turing machine, an arbitrary Turing machine, computes a function S. So this actually proves right theorem.